Here is a curve. It has this equation. Here is a point on that curve. It has these coordinates. Here is a tangent to the curve at that point. What is its equation? To the calculus capable, this is a trivial task. It's differential calculus 101. But while mathematics has been done since ancient times, calculus has only existed in its modern form for the last 350 years or so, a relatively recent invention, or discovery, however you want to look at it. What did mathematicians do before calculus? The story to answer this question is one of rivalry, two competing ideas posited by two intellectual titans of the pre-calculus era. In one corner, the proud and accomplished philosopher and mathematician René Descartes, who proposed a rigorous but messy circle-based solution. In the other corner, the mischievous and mysterious lawyer and judge Pierre de Fermat, who used similar triangles and a generous amount of hand-waving to budge his way to an impressively reliable and insightful solution. What were these methods? Why did these mathematicians oppose each other? And most importantly, we attribute the invention of calculus to Leibniz and Newton. But is it Fermat who ought to be credited? Join me as we answer all of these questions and more in a deep dive into this bitter mathematical rivalry. Like all the best problems in mathematics, it's simple, except it isn't. We take a curve and we want to know how steep it is. The problem is, the steepness is always changing. Lines are easy. We can formalize the notion of steepness as follows. How much do you go up or down for every single step you take to the right? This one has gradient 2, this one has gradient -1/3, and so on. Bigger number, steeper line. Lines are easy because no matter where you are on the line, the steepness is always the same. Here in the UK, the term gradient is used for steepness, but elsewhere the term slope is used. I'm going to stick to calling it gradient because I'm a 30-year-old Brit and I'm not about to change now. Things aren't so easy when we're looking at curves. Take this red curve here, for example. If I take one step to the right, then sure, I take 2 spaces up to catch up with the curve. But that's true for the blue curve as well. Yet our intuition is telling us that the blue curve is steeper, that it's changing directions, just generally misbehaving. Our intuition is screaming steeper, but in mathematics we seek to formalize our intuition. What numbers can I put on the curves at this point which encodes our intuitive understanding of steepness? Of course we know the answer. Draw a tangent to the red curve at this point. We define the gradient of the curve at that point as the gradient of the tangent line at that point. This is of interest because given any system that evolves over time, the gradient at a specific point measures how much the system is currently changing. Steep gradient, big change, and most systems found in nature evolve in these smooth, continuous ways. If you want more reasons why tangents are of practical interest, then I suggest finding another video because I'm a pure mathematician and the problem itself is interesting enough for me. Anyway, this became known as the tangent line problem. It was a problem because before calculus there was no good way of getting your hands on this tangent. This brings us to the 17th century and Descartes. Now we all know this guy. Our usual XY coordinates, Cartesian coordinates, are named after him. He thought, therefore he was. Descartes was very interested in the tangent line problem. In his work Geometrie, he writes, "I dare say that this is not only the most useful and most general problem in geometry, but even that I have ever desired to know." And he goes on to detail his own method, which we'll go into shortly. First, let's talk a bit about Descartes, because he is one of history's most, how can I put it nicely, confident thinkers. He was friends with Mersenne. Yes, that's Mersenne, the guy behind Mersenne primes, and in a 1637 letter exchange with Mersenne, he wrote, "I do not enjoy speaking in praise of myself, but since few people can understand my geometry, and since you wish me to give you an opinion of it, I think it would be well to say that it is all that I could hope for. I have only tried to persuade people that my method is better than the ordinary one." Nice. Unfortunately, we all know that the only thing worse than an arrogant person is an arrogant person who's right. His breakthrough in geometry was revolutionary. In ancient times, there was arithmetic, the study of numbers, and there was geometry. But their geometry all happened in the plane, with points and lines and circles just kind of floating in the ether. In the Middle Ages came algebra, but it took until Descartes to marry algebra and geometry together. to realize that algebraic expressions embedded on an axis actually define geometric structures. Any mathematician will tell you that uniting two disparate areas of mathematics often produces theory that's greater than the sum of the parts. Algebraic techniques can push geometric understanding, and geometric visualization can push algebraic methods, and so on. It's magic. So some credit has to go to Descartes for his breakthrough, even if he was a bit of a smartass about it. This new approach to geometry was called analytic geometry. So let's see it in action. Let's look at Descartes' solution to the tangent line problem. We'll look at the general case, and then we'll apply it to a specific curve, the one I showed you from earlier, y equals x cubed. Okay, so let's look at Descartes' method in some detail, because it really is quite interesting. If we look at this curve here, let's just say that this curve is some function of x, and we're going to pick a point, and we're going to find the tangent to the curve at that point. So let's pick this point here, and we'll call that point P. That's the point at which we're going to find the tangent to this curve. Now, the principle behind Descartes' method is as follows. We already know all there is to know about circles. We know how to find the tangent to circles. So let's introduce a circle. Let's draw the normal to the curve at P. Remember, normal just means at right angles to the curve. And it's worth noting here that we don't know what this normal line is. If we were able to find the normal at a general point to a general curve, then we've already solved the problem, because once we have the normal, we can then derive the tangent, which is really easy to do. So actually, we're just going to pretend that we know what this normal is for the time being, and we're going to say that this normal intersects the x-axis at some point V. And like I said before, we already know how to derive the tangent to a circle. So let's introduce a circle where the normal that we've just drawn is the radius of that circle. So we'll draw the circle in here. Okay, and now the tangent to the circle will also be the same as the tangent to the curve at that point. Okay, now remember, the overall goal here is to find the equation of this tangent line. How do we do that? Well, we know one point that the tangent goes through, so the only other piece of information we need is the gradient of the tangent. So how are we going to get the gradient of the tangent? Well, if we knew the gradient of this normal line here, this radius, then we could take its negative reciprocal, and that would give us the gradient of the tangent. So the goal now is to find the gradient of this line here. And how are we going to do that? Well, we can find the gradient of a line so long as we know 2 points that the line goes through. We know that it goes through this point P, and we know that it goes through this point V, except we don't actually know what the value of V is yet. But if we do work out the value of V, we know 2 points that we can then use to find the gradient. So the goal here is to find the value of V. So how are we going to find V? Well, as always, we start with what we know, and that is that we know that P lies on this curve and lies on this circle. So we can give two equations that the coordinates of P must satisfy. So first, we have that y equals f of x, it's a point on the curve, and we also have this, the equation of the circle. So already we can see that we can substitute y equals f of x into here to eliminate y, and I'm also going to rearrange it to set it equal to 0. You'll see why in just a moment. So in effect, we have created a polynomial for which the x-coordinate of P will be a root, which I'm going to call x0. So we can actually do something even more clever here, and that is to employ the factor theorem. So if x0 is a root of this, then x minus x0 will be a factor, and we know something even more than that. We know that it is not only a root, but because it's a tangent, it is a repeated root. So actually, x minus x0 all squared will be a factor. So we can take out a factor of x minus x0 squared, and this will be times some polynomial g of x. Here, we've established something that we should be able to solve. So that's the game. From here, we solve for v, which we can then go through these steps to derive the tangent. Let's see this in action. Let's get away from the abstract general method and we'll look at a specific example. So as I said before, we're going to choose the specific example y equals x cubed. You're just going to have to use your imagination and imagine that this is in fact a cubic curve. It's not too bad. And then the points P I'm going to specify as 1, 1. So x0 will be 1. Okay, so let's deploy this formula here. So this tells us that r squared subtract x minus v all squared, subtract f of x squared. Remember, f of x is x cubed now, and this is equal to x minus 1 all squared. Remember, x naught is 1, multiplied by g of x. Now we're going to expand and simplify this left-hand side. I'm not going to go through every step here because it's fairly straightforward. I'll just skip to the end. I'm also going to expand this bracket here. And now, what on earth do we do with this? Well, we realize that on the left-hand side, we have an order 6 polynomial, and on the right-hand side, we have a quadratic order 2 polynomial multiplied by some polynomial, but because the orders have to be the same on both sides, we reason that g of x must be a quartic polynomial, that is an order 4 polynomial. So let's write a general form for g of x and then derive what it actually is. Now, this left-hand side is identical to the right-hand side, so we can compare coefficients in order to derive the coefficients of g. So the coefficient of x to the power 6 is the same on both sides. That implies that this here, this negative 1, is the same as the x to the power 6 term on the right-hand side. Remember, the right-hand side, I've written it kind of awkwardly here, but the right-hand side is this line here, and I'm going to say that the left-hand side is this expression up here. Okay, so how do we get an x to the power 6 on the right-hand side? Well, the only way to do that is to times x squared by a4 x to the power 4. So this must be, in fact, equal to a4. Okay, great, we've got one of our coefficients already. Let's keep going, because this is always a fun game. Let's work down the powers. Let's go with x to the power 5 next. So there is no x to the power 5 term on the left, so we're going to write 0 here. And then the coefficient of x to the power 5 on the right, well, there are two ways of getting an x to the power 5 term on the right. That's to do the linear times the quartic, or to do the quadratic times the cubic. So we've got minus 2 times a4 plus a3. And remember, we already know that a4 is negative 1, which means this whole thing is positive 2, which means that a3 is negative 2. And from here, we're going to go ahead and work out all the coefficients of g of x. I'm not going to go through all of the details here, but all the details are written down if you want to work alongside me and check you're working. And eventually we reach this stage, which is where the magic happens. We have the coefficient of x on the left-hand side being equal to 2v, and the coefficient on the right-hand side of x is going to be 1 times a1, subtract 2 lots of a0. We know that a0 is minus 6, so this whole thing here is positive 12, and we know that a1 is minus 4, so minus 4 plus 12 is 8, and this implies that v is equal to 4. Why do we care about that? Well, we're done. We said that if we find v, then we get the answer. So let's do it. We've essentially worked out that the normal line is going through 1, 1 and 4, 0. So the change in y is negative 1 and the change in x is 3. So that is the gradient of the normal line. This now tells us the gradient of the tangent because we take the negative reciprocal of this, just flip it and negate it. So we have a gradient of 3, and now we can use that to derive the equation of the tangent. That is a line with gradient 3 that passes through 1, 1, so it doesn't take long to work out that the equation must be y equals 3x subtract 2. And that was Descartes' method for finding tangents. So what do we think about this method? Well, I think it's quite ingenious, the idea of introducing this circle, because you're introducing something that you already know about. But I think we can agree it's quite long. It's very long-winded. It involves a lot of kind of calculation, and you can imagine, instead of y equals x cubed, what if we had something even scarier here? The calculations would become even more burdensome. Now, this was detailed in his Geometrie, which was the third of 3 essays published in his 1637 work, Discourse on Method. It's in the introduction to this work where we find the famous cogito, I think therefore I am, as he outlines his philosophy of rationalism. Now, Descartes was already a well-established and highly regarded philosopher at the time, and this work was to be a culmination of many of his best ideas. Now, the first of these essays was called Dioptrics, and here he discusses light and concludes some funky ideas that light travels at a near instantaneous rate and travels faster through denser media like water. But anyway, another mathematician and lineographer, Jean de Beaugrand, managed to obtain an advanced copy of Dioptrics the spring before it was set to be published, and Beaugrand shared it with many other mathematicians who all had things to say about it. And boy, did Descartes have things to say to them. So this is where we pause the story of Descartes and introduce his future rival. So, Pierre de Fermat is perhaps best known for his work in number theory, proving results like Fermat's little theorem, and claiming to have proved results like this one, Fermat's last theorem. As the story goes, he wrote in the margin of his book that he has a wonderful proof of this result, but that it is too long to give here in the margin. Given that it took another 350 years and the invention of several new branches of mathematics on the obsessive mind of Andrew Wiles, who secretly worked on a 100-page proof in his attic in secret alone for 6 years, it is generally understood that Fermat's proof was wrong, or that he didn't have one and he was just making a joke. But while Fermat is known for these developments, it could be argued that his most important contributions to mathematics lay in the tangent line problem. Now, while we think of Fermat as the mischievous scamp who was too lazy or too cheeky to give us his supposed proof, he was apparently a much more tentative mathematician. See, Fermat was a mere mathematician hobbyist. He actually pursued a career in law and was later appointed as a judge in Toulouse. But he harboured a fascination with ancient scholars and set about restoring their mathematical works. Yet he was always reluctant to publish his mathematical works lest he open himself up to criticism, and he had a reputation for writing without detail, loosely, skipping steps and so on. I suppose in that way he'd be right at home in modern academia, where many of the steps in proofs are left to the student. Despite this, he did earn renown as a powerful mathematician, beginning a correspondence with Jean de Beaugrand and other Parisian mathematicians like Mersenne, Pierre Petit, and others. So it was then that Fermat obtained the advanced copy of Descartes' Dioptrics from Beaugrand. Along with many others, he was highly critical of the work, and he wrote his criticisms in a letter to Mersenne, who was destined to become the intermediary throughout this slugfest. Mersenne apparently held on to the letters for a good few months before plucking up the courage to send them to his good friend Descartes. It's actually fairly tame. It's good to search for the truth, and we often find it by groping in the dark, so perhaps his offerings may be useful, and perhaps someday he'll be able to build them into something good. Now, this isn't a video about Dioptrics, so I'll just summarise here. The critics mostly challenged Descartes' assumptions and claimed that much of his reasoning was circular. Now, what was Descartes' reputation in terms of how he responded to criticism? Well, I am positively pleased when they attack my works, because I see them as like flies that always go for the best fruit. He would later go on to nickname Pierre Petit Little Dog, and as for Jean de Beaugrand's letters, don't send any more, because we already have plenty of scrap paper, which is all they are good for. Seriously, this guy. I beg you once more not to send me any more objections, or at least don't expect me to compose any more replies addressed to people who aren't able to learn. Perhaps Descartes would be right at home in modern academia as well. Given that that was Descartes' reputation, when Mersenne did eventually send the criticisms from Fermat to Descartes, how do you think Descartes responded to this outsider, a mere amateur mathematician? Well, as you can imagine, Descartes responded with dignity, civility, taking the criticisms on board, and he responded to Mersenne to claim that Fermat was a deficient mathematician who owed much of his success to Descartes' own work. Now, where did that statement come from? Well, as it turns out, Fermat had also developed his own analytic geometry. Indeed, a manuscript of Fermat was circulated the same year, but the work it contains could be traced back to his earlier work in 1629. It is generally accepted today that both men developed analytic geometry independently. But, given Fermat's reluctance to publish, history remembers Descartes as the first. Had Fermat published first, we might be calling them Fermian coordinates. Fermatian coordinates? Fermish? Fermite? Who comes up with these anyway? Imagine I proved a theorem on this channel. Would it be another Ruffian? Ish, no, that doesn't sound good. As for Fermat's responses to Descartes, it's a bit of an open question as to the sincerity of some of his statements. Listen to this letter to Mersenne and decide for yourself. I assure you that it is not due to envy or rivalry that I continue this little dispute, but only to find the truth. I think Descartes will not believe me of ill will, since I am well aware of his outstanding ability. It's easy to interpret this as a sincere expression of admiration or as a bit of dry sarcasm. Shortly after, Fermat published his work Treatise on Maxima and Minima and on Tangents. Got to live those titles in the pre-YouTube era. Published today, you can imagine what it might say. Anyway, this is where we find Fermat's approach to the tangent line problem. So let's explore that now because, man, it is fascinating. If you don't know calculus, you'll be able to follow along just fine. This was, after all, before calculus. But if you do know calculus, prepare to be astonished by what Fermat was able to come up with. We'll look at the method in generality first, and then so that we can compare it to Descartes, we'll apply it to the same curve, y = x cubed. Okay, so on to Fermat's method, and let me just say I love this method. I had so much fun researching this video because it really just blew my mind. I'm so excited to share it with you. Anyway, so we're going to start like we did with Descartes' method, and we're going to look at a general curve y = f of x. And before we even get stuck into this method, we're going to do something a little bit strange, and we're going to rename this curve big F of xy. Equals 0, where big F of xy is equal to y minus f of x. F of xy equals 0 defines the exact same curve as y equals f of x, because all we've done is rearrange this one to equal 0. So we haven't really done anything, we've just written this in a more implicit form, and that's going to come into play later. So we're trying to find the tangent at a general point, so let's give ourselves a point to work with. So this is point P, and let's say that the coordinates of this point P are simply just x, y. Okay, nothing crazy so far. So let's draw in the tangent, and my diagram has ended up looking not very neat over here, but it doesn't matter. You know, back in the 17th century, they didn't have graphing software, they just had to use pen and paper, so let's just live with the imperfections. We are going to say, a bit like with Descartes' method, that this tangent intersects the x-axis at some point V. And we're going to pick another point here that's a distance of a away from x. So this will in fact be the point x plus a. And then this point up here we're going to call y1. Okay, now here is where some of the magic happens. Pay attention to these two right-angled triangles here. We've got one right-angled triangle defined between v and x with the tangent as its hypotenuse. And we've got another right-angled triangle defined between v and x plus a, again with the tangent as its hypotenuse. So because these angles are the same in both triangles, they are in fact similar, and we can use that to our advantage. This first triangle here, it has a base of length x minus v, and it has a height of y. And this larger triangle, this one has a base of x plus a minus v, and it has a height of y1. Now we're about to use the properties of similar triangles to derive an equation, but before we do that, let me just give you a quick snapshot overview of what it is that we're actually trying to achieve. We're trying to find the equation of this tangent here, and we know the equation of a line so long as we know 2 points through which it passes. We know it passes through this point P, which is on the curve, so we know what it is, and we're saying that it goes through the x-axis at some point V. As long as we know what v is, we can derive the equation of the line. So the objective is to find v. Since that's our objective, we want to set up an equation that involves v that we can solve for v. So let's do it. We know that these two triangles are similar. So that means the ratio between these two sides is equal to the ratio between these two sides. And now we're going to rearrange this in terms of y1. And what I'm going to do is I'm going to skip a few steps here. We are going to multiply up by x plus a minus v, and then we're going to split it up and simplify in order to get it into the following form. We have y multiplied by 1 plus a over x minus v. Now here is the magic of Fermat's method. We now have an expression for this y1 out here in terms of x and y. The problem is we still don't know what this value a is. This was an arbitrary value that we just chose at the very start of this calculation. A could be 1, it could be 1,000,000, we don't know. But we're going to assume that a is very small, and the smaller a is, the closer it is to this point over here. And therefore, the closer these 2 points are together. So at the moment, there is some distance here. But if we choose a to be very, very small, the distance between these 2 points becomes almost negligible. So negligible, in fact, that we're actually going to say that this point is approximately equal to the following: big F of x plus a, comma, y1. And we're just going to assume that these points are pretty much the same, that y1 equals small f of x plus a, therefore this point corresponds to big F of x plus a, y1. So at some stage of our calculation, we are going to need to account for the fact that we're taking a to be pretty much 0, and we'll get to that in just a moment. For now, let's just finish the setup. So we have big F of xy must equal 0 for all points on the curve, but also that big F of x plus a, comma, y1, and we have an expression for y1, it's this, y1 plus a over x minus v, and both of these hold and will allow us to solve for v. So let's see this in action, and so that we can compare it to Descartes' method, we'll choose to apply it to the same situation, y equals x cubed, at the point P, 1, 1. So this is the form y equals small f of x. We're going to rewrite this in terms of big F of x, and then we're going to make this substitution, and at some stage we want to let a equal 0, because this corresponds to bringing these points arbitrarily close together. And that's the key to this entire method. Let's see what it looks like in practice. Instead of writing it y minus f of x, I'm actually just going to write it as f of x minus y. The situation is exactly the same, it's just going to make something a little bit easier further down the line. And remember that f of xy equals 0 defines the curve. So now let's look at this horrendous thing over here. This function is saying take your first thing and cube it, and then it says subtract your second thing. Okay, and now what? Well, we're going to expand, and we're going to get a little bit of cancellation. Sneaking in here, we've got an x cubed subtract y, and we know that x cubed subtract y equals 0. So those terms actually die. Okay, and now notice that a is a member of every term. And this is what Fermat talks about in his method. You need to, at some stage, divide through by a wherever possible. So you want to eliminate the number of a's in your expression. So we are going to divide this entire thing by a. Okay, and then it's at this stage where we're going to bring this idea back into play, the idea that we set a equal to 0. And that's the resulting equation. And remember, we're doing all of this in an effort to find v. So let's rearrange this for v. Again, I'm going to skip a few steps here, but this turns out to be that v equals x subtract y over 3x squared. And at this point we realize we've made this a bit more difficult than it really needs to be, because we know the value of x and y. It's 1, 1. However, I intentionally didn't do that because I wanted to show you that the power of this method is that it gives us a general expression for v. If we now decide we want to work out the tangent at a different point, we can make that substitution here and we can derive the value of v and then therefore derive the equation of the tangent. So this general form reveals the true power of this method. But let's go ahead and finish by working this out at the point 1, 1. So v in this case will be 1 subtract 1 over 3, which is 2/3. So our tangent line passes through 2/3, 0, and 1, 1. So the change in y is 1, and the change in x is 1/3, which gives us a gradient of 3. And then from here, we can derive the equation of the tangent. It's got gradient 3, it passes through 1, 1. So we work out that the equation of the tangent, as before, is y equals 3x subtract 2. So what do we think of this method? Well, as I said before, I kind of love it. There is some magic that goes on with this term a, which we will talk about shortly. But it's hard to deny that there is some real insight going on in this problem, and we'll discuss that more a little bit later as well. Now, it probably won't shock you to learn that Descartes thought his own method was superior. Fermat backed his own method, but was eager to hear what Descartes had to say. He even wrote to Marcia requesting comments. I await his remarks on my work. If there is some rancor, that should in no way keep you from showing them to me. It's almost like he's saying, come at me. Descartes, on the other hand, denies that any hostility is his doing, as he writes in another letter to Marcia. I beg Fermat's defenders to believe me that if they are right that there's some personal animosity between him and me, it comes entirely from his direction. When I see that Fermat has friends that work hard to defend him, I conclude that they are drawn to him by some attractive characteristics he has. Attractive characteristics? If only they weren't enemies, this could have been the beginning of something very beautiful. Descartes went further and criticised Fermat's method. He didn't like the notion that in one instance we're dividing by this term here, and in the next instance we're equating it with 0. Which is it? Because if it's both, we are in effect dividing by 0, which is a little bit spurious. Fermat defended his method. I maintain that my methods are just as certain as the construction of the first proposition of the elements. Perhaps having them put forward naked and without demonstration, they were not understood, or they appeared too simple for Descartes, who has taken such a difficult path for these tangents in his geometry. For what it's worth, I agree with Descartes' critique. There is a kind of loose nature to Fermat's method, where we just kind of do a bit of magic and hope the right answer pops out. But it's hard to deny that Fermat's method is the superior one in terms of its simplicity and in the ideas that it contains. All this culminates in a challenge that Descartes set Fermat to expose the weaknesses in his method. There is a curve which, because of this history, became known as the Folium of Descartes. Folium is the Latin for leaf, and as you can see, the curve looks exactly like a leaf. Descartes was unable to find the tangent to this curve at a general point, and wanted to prove that Fermat's method fared no better. So let's look at this curve in a bit more detail. Let's see why Descartes' method broke down, and let's see Fermat's response. Okay, so this curve is the Folium of Descartes, and it has this implicit formula here, and it does have this constant d, and changing d just like warps this curve, so it doesn't really matter what d is. So before we start, we're actually just going to make life easier for ourselves by choosing the specific case when d equals 1. It doesn't matter what value of d you choose, you can even do it in the general case if you want to, but the mathematics is the same regardless of d, so we're just going to simplify things a little bit by looking at the d equals 1 case. So let's begin by examining why Descartes' method breaks down. So we're going to attempt to find the tangent to the curve at this point p here, but p is arbitrary, just bear that in mind. And recall that the first step in Descartes' method is we actually draw a circle such that the radius of the circle is a normal to the curve, and therefore a tangent to the circle is the same as a tangent to the curve. I'm going to call this value here u, where the normal intersects the x-axis. Earlier I called it v when I talked about Descartes' method, but I'm going to call it u because I'm going to also have Fermat's method on this diagram, and I'm going to use v for Fermat's method. So remember that the idea here is that we have the following equation for the circle, and then we also have that y is equal to f of x. That's the equation of the curve. So then we substitute that into here, and then we reason that the x-coordinate of p, which I'm going to call x0, is a repeated root of this polynomial, and therefore I can take out a factor of x minus x0 all squared, multiplied by some polynomial g of x. But already we can see the problem. We can't get our hands on this f of x because this is an implicit function. There is no way to rearrange this and get y equals something, so unfortunately this is where the method breaks down. And this is why Descartes thought that it wasn't possible to find the equation of a tangent at a general point to this curve, because this is an implicit function. And in fact, the more you look at Descartes' method, the more you see issues with it. The particularly astute among you might have noticed some erroneous reasoning going on in Descartes' method, and that's when I said that this over here is a polynomial so that we can invoke the factor theorem. But who's to say that this is a polynomial? This is only a polynomial if f of x is a polynomial, but as we know, there are many non-polynomial functions out there. What if we had an exponential function, or f of x equals the sine of x? So this whole method really breaks down as soon as you get to an f of x, which is either not a polynomial, or as soon as you get to an implicit function. Alright, bad luck Descartes, but does Fermat's method fare any better? Let's look at that now. Okay, so hopefully you recall the setup here. I've got a point that I'm going to call Q with coordinates x, y, and that lies on the curve. And then we go out to another point, x plus a. I'm going in the negative direction here, but it doesn't matter. We can just take a to be negative. And we call the point where it meets the tangent y1, and then we kind of fudge it and say that y1 is basically on the curve when a is very small. So just to recap, we say f of x, y is equal to 0. And here we have f of xy equal to x cubed plus y cubed minus 3xy. And we also say that f of x plus a, comma, y1, and we have an expression for y1, which, if you recall, is y times 1 plus a over x minus v, and we say that that is equal to 0. So let's do the algebra. So this function is saying you take your first thing and cube it, so we have x plus a cubed, and then it's saying take your second thing and cube it, and then it's saying subtract 3 lots of your first thing and times your second thing. And remember, we're looking for 3 things. Firstly, we want to use this at some point in our working, because this is the curve that we are talking about. At some stage, we want to divide by a, and then at the third stage, we are going to set the remaining a's equal to 0 to illustrate the idea that we're bringing these points arbitrarily close together. So let's do a bit of algebra. So I'm going to expand this x plus a all cubed, and I'm going to write it in a specific way, and you'll see why in just a moment. I'm going to say this is x cubed, and then I'm going to factor out the a from the remaining terms. So this is a lots of 3x squared plus 3ax plus a squared. And then for the next term, I'm going to do something similar. Imagine cubing this whole bracket. The first term is going to just be a 1. So I'm going to take that on the outside. It'll be y cubed times 1. And then we're going to have y cubed in the mix with the rest of it. But like I did with this bracket, I'm going to factor out the a. And again, with this final set of brackets, I can see that I'm going to get a minus 3 times x times y times 1. So I'm going to pull that out to the outside. And then we can see that the rest of the terms are going to have an a involved. And they're also going to be times by minus 3, so let's keep that on the outside as well. Now, why have we expanded it like this? Well, as my maths teacher used to say, there's method in the madness. We have an x cubed plus y cubed subtract 3xy, and we know that that is equal to 0, so those terms die. And since this whole thing is equal to 0, which I should have said from the very beginning, we can actually divide through by a, which is easier to do because we've factored out the a from many of these terms. And even more than that, what we're going to say is any remaining terms with an a, we're not going to bother writing them because we're going to set a equal to 0 in the next step. So all of these terms here are going to die when a equals 0. So what are we actually left with? And there is a common 3 here, so let's just divide through by that. So before we go insane with all of the algebra, let's remind ourselves what it is we're trying to do. We're trying to get our hands on v. With v, we can derive the equation of the tangent. So the last thing that we need to do here is simply to make v the subject of this equation. And we'll start by multiplying through by this denominator x minus v. I ran out of space, so I'm going to start a new line here. We have x minus v multiplied by x squared minus y. Plus y cubed subtract xy is equal to 0. And then I'm going to cheat and skip a few steps here. I'm going to subtract y cubed from both sides. Remember, that should be negative. And then I'm going to add xy to both sides. Remember, that should be positive. And then we'll divide by this x squared minus y. And then we are left with x minus v on this side. But then I'm going to multiply both sides by minus 1, which restores these terms to y cubed minus xy. And this becomes v minus x. In other words, I can add x to both sides, and I'm done. I suppose it is a bit neater if we write it as a single rational function, so let's multiply x by x squared minus y so that we can add the fractions together, and what we are left with is x cubed plus y cubed subtract 2xy all over x squared minus y. So this is a general formula for v, where a tangent line crosses the x-axis. If we picked a concrete point Q and substituted its coordinates into here, that would give us the coordinates of v, which we can then use to derive the equation of the tangent. And while we're here, let me show you something that's really going to blow your mind. Let's say that we wanted a general equation for the gradient of this tangent line. So in other words, we need to do the change in y over change in x, where we're going to take the difference between the point v and this point here, which is q. So the change in y is going to be y subtract 0, because that's the y coordinate of this point V, it's on the x-axis, and the change in x will actually be x subtract the x coordinates of this whole thing here. Don't be afraid, it actually turns out quite nice. Okay, bit of a nightmare, but let's simplify. So first of all, the numerator is obviously just y, and then we can multiply x by x squared subtract y. So we get x cubed subtract xy, and then we subtract x cubed, subtract y cubed, plus 2xy, and this is all over x squared minus y. And this is all under y. Okay, now whenever we divide by a fraction, we're just going to invert the fraction and multiply. So the numerator becomes x squared y subtract y squared. And then in that denominator, we get some cancellation, our favorite. So x cubed, they're going to die. And then the minus xy plus 2xy just becomes xy. And we have a subtract y cubed. And I'm going to simplify further by dividing numerator and denominator by y. And I'm justified in doing that so long as y isn't 0. So I'm just going to say I'm going to take a general point Q for which y isn't 0. The only point on the curve for which y is 0 is at the origin. And you can see here that the tangents are the axes anyway, and that there isn't one clearly defined tangent. So let's just take a point Q, not the origin. So we'll divide by y and we end up with this. X squared subtract y all over x subtract y squared. Okay, put a pin in that for a second because I promised this would blow your mind, and it will. Let's jump ahead to modern day where we do actually have calculus. Let's use calculus to find the gradient function of this. So we just need a bit of implicit differentiation here. So we do 3x squared plus 3y squared dy by dx, and then we use the product rule, so we subtract 3x lots of dy by dx, and then subtract y lots of the derivative of 3x, so subtract 3y. Okay, there's 3's all over the place, so let's divide through by those, and then a bit of rearranging. So let's add y to both sides, let's subtract x squared from both sides, and then we divide by y squared subtract x. And we can multiply numerator and denominator by -1. It does not change the expression at all. But what it does give us is the exact same thing that we had over here. So, using Fermat's archaic method, we are still able to find the general formula for the gradient of a tangent. And isn't that just the best? So, in a way, Fermat won. His method succeeded where Descartes failed. As for how their feud continued, Fermat became more prolific, and Descartes would later bemoan the quantity of results that Fermat had proved. They have sent me a great register of Fermat's discoveries, but this, rather than making me think better of him, has reminded me that it's the poor man who counts his sheep. You just cannot win with Descartes. And in yet another letter to Mersenne regarding Fermat, this one's my favourite. I have seen many of his writings, in which I have found 2 or 3 good things mixed in with many bad ones. I think of them in the same way Virgil thought of Ennius, when he extracted little bits of gold from his works under the title The Dung of Ennius. But Fermat didn't let things go without a rebuttal. He grew increasingly frustrated that Descartes' ideas enjoyed much more acclaim and popularity. Shortly after Descartes died in 1650, Fermat had this to say: "I would be delighted if the differences that I have formerly had on this subject with Descartes were ended to his advantage. I would have been satisfied in all ways. The glory of a friend whom I have infinitely esteemed, and who has passed with good reason for one of the great men of his time." Again, it's hard to judge the sincerity of these words, and as historian J. Nicholson points out, Fermat always wrote formally and with politeness, perhaps obscuring the hatred he felt towards his rival. He argues, for example, that Fermat calling Descartes one of the great men could imply that he's calling Descartes one of the fattest and most pretentious men. Fermat continues to say that the pursuit of truth is much more important than winning an argument, as this seems incomparably more valuable than winning my case. I put myself, therefore, in the posture of a man who wants to be vanquished. I say it loudly, I bow at last to your superior powers. Easy to see traces of sarcasm, and Nicholson again also notes that I bow at last to your superior powers is the first line of a poem, Epode 17, by Horace, which tells the story of someone doomed to forever endorse the fame of someone else. So while Descartes was very direct in his derision of Fermat, there is a case to be made that Fermat's criticism was much more subtle and wrapped up in the formal language and etiquette expected of someone of his social standing at the time. Now, the calculus capable among you have probably noticed a striking similarity between Fermat's method and differentiation from first principles. There are the faint glimmers of the notion of limits in this method. His final step of just set this term to 0 feels like we're taking limits, and indeed, in the continuous examples we've considered, the limits do happen to align with taking the value at 0. But in Fermat's work and in his time, it hadn't quite been formalized. Never did he take a general curve and produce its derivative, for example. And while he did work on the area under curves, the foundation of integral calculus, he never noticed that the two concepts are intimately connected, as in the fundamental theorem of calculus. These ideas were developed a little later by Leibniz and Newton, and because these notions are so essential to calculus, it can't quite be said that Fermat invented calculus first. I think it is fair to say, however, that I think he was very close, and that his ideas, more than Descartes', planted the seeds for what would eventually become calculus. As for whether Newton or Leibniz invented calculus first, that's a story for another video, but Newton himself wrote that his own ideas about differential calculus were directly inspired by Fermat's way of drawing tangents. So while we know Fermat as the last theorem guy, perhaps he deserves to be known better for laying the foundation for calculus, for providing a shoulder upon which Newton could stand. Thank you so much for watching. Yes, in case you were wondering, these are the same bricks that I used in my series on set theory. If you haven't watched those videos yet, you should definitely go and check them out. Thanks for your patience on this one. I didn't mean to take so long, but as soon as I was ready to start filming, I got hit with a really bad case of COVID. I even briefly had to visit hospital. The symptoms were so bad. Please take COVID seriously, because even if you're like me and you're young, you have no previous health conditions, it can be really bad. An enormous thank you to my Patreon supporters. As you know from all the updates, my life is a little bit up in the air. It's a bit of a strange time for me right now. Your support has never meant more than it means now. So from the bottom of my heart, thank you for that. And I love just having that Discord server where we can hang out and bounce ideas around. It's great. If you'd like to support me on Patreon, you'll find the link below. If you're not able to, don't worry about it. Subscribe and share the video. That'll really help me out as well. Anyway, before I go off on another tangent, this has been another proof under another roof. Have a nice day. Cut.